We shall now take up a detailed discussion of the three important crystal structures into which most of the metallic elements crystallize. The first one being the cubic closepacked crystal, the second one being the BCC crystal, and the third one being the hexagonal closepacked crystal. Often we call, as we know, the CCP crystal, the cubic closepacked crystal, also as the FCC crystal. But we should note that this is a what you might call a rather casual usage, and therefore often we have to differentiate the various kind of crystal structures which are based on the FCC lattice. We shall also consider the fourth crystal, the diamond cubic crystal, even though there are no metallic elements which crystallize in this structure. Additionally, we shall play importance to the interstitial positions, the voids in these crystal structures, and we will see how various for instance elements can fit into these interstitial voids and give us interstitial alloys. So this will be the focus of the next set of discussions, and peeking ahead we will see what are the kind of considerations we will keep in mind. We will see that the cubic closepacked and the hexagonal closepacked crystals are close packed. When I use the word or the term or the phrase close packed, what I imply is that it is the closest packed. If you have spheres of all same size, the closest packing which you can obtain is 74%. That means 74% of space can be occupied, and these two crystal structures have that packing fraction or that percentage packing as 74%. It is important to note, as we shall of course see in detail later, that the voids found in these two crystal structures are the regular tetrahedron and the regular octahedron. The coordination number, as we shall see, the coordination number being the number of atoms surrounding any central atom, which are usually touching the atom, and in some cases they may not be actually touching the atom, because the coordination polyhedron is a polyhedron formed by atoms around any central atom, and it could involve atoms other than the nearest neighbors. The coordination number for both CCP and HCP is 12, and you can have no higher number than 12 for any configuration of equal size spheres. As we shall see, the coordination polyhedron for cubic closepacked is the cube octahedron, and for the HCP is the twinned cube octahedron. We will also note the BCC crystal is not a closepacked crystal. That means its packing fraction is less than 0.74. It does not have any closepacked planes, but the 111 direction in the BCC is actually a closepacked directions. The voids in BCC are not regular polyhedra like the tetrahedra or the octahedra. On the other hand, they are neither fully distorted, so we can call them non-regular tetrahedron, the non-regular octahedron, and we will see the shapes of these polyhedron. The diamond cubic structure is not a close-packed structure. It has no close-packed planes or close-packed directions. We had mentioned this briefly, but we will revisit the concept again. So let us try to understand how do we form the cubic close-packed structure, starting with, for instance, single atom, then with a row of close-packed spheres, then going on to a plane of close-packed spheres, and finally to the three-dimensional structure, which is the cubic close-packed structure. So we already have noted that the CCP crystal is obtained by monoatomic decoration of the FCC lattice. So let us start with the row of atoms. Of course, you could start with a single sphere, then we make a close-packed row of atoms. Then starting with this row, by putting these rows one below the other in the fashion shown here, I can obtain a hexagonal close-packed layer. Of course, I call it hexagonal because this layer has got hexagonal symmetry, and you can see once the layer has been formed, it has got close-packed directions, and as we shall see later that these close-packed directions, when you correspond it to the cubic directions, then this will be correspond to the 110 type of directions. So this is a close-packed direction, this is a close-packed direction, this is a close-packed direction, and this layer has got hexagonal symmetry. And for instance, around this point, if I rotate 60 degrees, then the structure will remain invariant. Now this layer itself, we will see that actually becomes what, according to the cubic indices, will be the 111 plane of the cubic crystal. Now to build the next layer, which will actually lead me to the three-dimensional structure, there are two stable positions. For instance, suppose I call all the atomic positions in this layer as the A layer. That means this green sphere, or for instance in this case the blue sphere, is the A position. This will also be the A position, this will also be the A position, and so forth. Now once atoms are present in the A position, there are two other stable positions where I can put atoms to make the second layer. For instance, this would be the B position, and then this would be the C position. Now suppose I start putting atoms in the B position, suppose I put a sphere here, then I will not have enough space to actually put an atom of the same size or the sphere of the same size in the C position. That means if I have chosen B in the second layer, then I can put one sphere here, one sphere here, and one sphere here, which will all be the B positions. Alternately, I could put a sphere in the second layer in C position, which means that I cannot put a sphere in the B position. I can put one in the C position here, I can put one in the C position here, and one in the C position here. So I have two choices for the second layer, and I can construct a second layer by putting atoms in the way I have told. We will actually show these things, revise these things again with actual physical models, so that the concept of space filling becomes absolutely clear, but we have these choices for the second layer. Now having constructed an A layer, suppose I choose my second layer to be the B layer. That means I put atoms in this position, and this position. So I have put atoms in the B layer, then I have marked them by green color, then I can propagate this entire two-dimensional plane, and each one of these planes independently, not in combination but independently, has a 6-fold symmetry. So even though I have shown it as a triangle, actually this layer and this layer are no different, they are both hexagonal layers, and I can put this layer. Having put the B layer, again I have two choices. I can put a sphere directly above this sphere which I put in the A layer, that means the sphere will sit in the A position, or I have an alternative that I could actually put a sphere in the vacant C position. That means I have already put an atom in the A position, the second layer is the B position. For the third layer, either I can go directly above the A layer, or I can put it in the vacant C position. To obtain the cubic close-packed crystal, I will have to use the alternative C. That means the first layer I call A, the second layer B, third layer C, and therefore my packing would look something like this. So this is my A layer. If you look at the diagram on the right hand side, the B layer is the green layer, and the C layer is the layer which is originally was left vacant. So each one of these layers is actually a hexagonal layer, exactly identical to the layer shown in this diagram, the blue layer here, and I can put these three layers together. Now this kind of a packing of three layers, I can repeat again. That means the fourth layer I put would be exactly above the A layer, the fifth layer would be exactly above the B layer, the sixth layer would be exactly above the C layer, and so forth. Therefore such a packing would be called the ABC, ABC, ABC packing, and the crystal I obtain in this case would be called a cubic close-packed crystal. Now the same thing is shown in certain projection here. For instance, you have the C layer, then you have the B layer, and you have the A layer. So in the A layer, for instance, the spheres would go into the voids formed by the B layer. Of course, this atom is shown in different color just for identification. All spheres are identical as far as the crystal goes, and the C layer would go into the void which is not formed by the now formed the B layer, but in a different void. Now if you look down the direction, that means I am now looking like exactly the way I did, looking down this direction, which is perpendicular what we as we shall see to the 111 layer of the cubic crystal. So this is my 111 planes which I am constructing now. So this will be my A layer, the B layer would be the ones shown in the blue color here, and finally the C layer would be the layer shown in the green color, and finally I have the layer below that as the A layer. So if I color all my spheres identically, which is what they are identical species, then I would have a packing along the 111 direction which looks like this. Now as I said, we will look at this construction once again in detail using models, but before that let us look at what we call the conventional unit cell and try to correspond it to the packing which we have just now considered. Now we already know the lattice is FCC and the motif is a single atom or ion at, for instance, 0, 0, 0. Now I want now correspond my picture of ABC packing with the conventional unit cell of an FCC, which I have already considered before. Now the way of constructing is actually constructing along the vector connecting the A to the A atom, which is now my 1, 1, 1 direction. So the AA vector, the direction connecting my A to A is the 1, 1, 1 direction, and I am trying to construct my crystal along that direction. So you can see that the A exists, then there is a B layer which is now made by these B spheres, then there is a C layer, and finally there is one more A layer. So in other words, I am constructing my crystal with respect to this orientation, the standard orientation of the FCC crystal along the 111 direction. And what I get, as you know, is a quadruply non-primitive unit cell which has 4 atoms per unit cell. Now this diagram again tries to clarify the same point, that I have a C layer. Of course in this case I had called that the A layer, but it is just a nomenclature. Therefore I have a layer here, then I have the next layer which is the blue layer, again consisting of spheres in hexagonal configuration. Then I have this green layer which again consists of spheres in hexagonal configuration, and there is a final layer which also is centered around this, but also has got atoms in hexagonal configuration. Now when I do this kind of a packing, it is not surprising that the crystal I generate has got not 6-fold but 3-fold. The 6-fold original layers had 6-fold symmetry, but this ABC packing has destroyed the 6-fold and has left us only with a 3-fold rotational symmetry. In fact, you can also visualize this symmetry as not just a mere, in simple rotation it is 3-fold, but in terms of a roto inversion actually it is a 3-bar axis. So this CC axis actually is a 3-bar axis, and if you want to look at a simple rotational axis, it is a 3-fold axis. Now so far it is easy to understand because 3-fold is a subgroup of the 6-fold symmetry, and therefore that is what survives during this packing. But what is surprising which arises during this kind of an ABC kind of packing is the existence of the 4-fold. Now we are doing the packing along this 3-fold direction, which is the vector we have shown here, which is the direction of the packing of the ABC layers, but surprisingly at an angle of about 54.74 degrees to this 3-fold axis, you get a 4-fold axis. And this aspect is not obvious when you try to do this packing, but this is generated purely by this kind of a packing, which is the ABC kind of a packing. Before we take up the unit cell of the primitive unit cell of the FCC crystal structure, we will try to understand the same concepts which I mentioned here using models. What I have got here, as you can see, is a hexagonal layer of atoms. This is the closest packing I can get in 2 dimensions, and all spheres are touching each other, and as you can see, this axis for instance is an axis of 6-fold symmetry. To understand my ABC packing, I will take a part of this whole hexagonal structure, which is nothing but a small section here which has got 7 atoms. Now this 7 atoms I call the A layer. So these atoms belong to the A layer. Now I have 2 options. Either I can put a sphere in here, which I will choose for instance a green sphere to show you, or I can put a sphere in this position, the other position which is remaining here. So I have option for the second layer is here or here, but not both. So let me label those. So let me label these 3 as the B positions. So I got 3 B positions, and then additionally there is a possibility of putting atoms in C positions. So let us look at the structure. So I got the A layer, then for my second layer I can either put atoms in the B position or the C position, but I cannot put atoms in both the positions, because now if I put atoms for instance in this position, then there is not enough space to put it here. Therefore if I put atom in the B position for instance for the second layer, then I can put atoms continuously in the B position. So this is my B position has been filled. Still my C positions are vacant, like you can see here, and I can put an atom in the third layer either directly above the A layer, which is one option, in which case I would take a for instance a sphere like this and put it right above the A layer, or the other possibility is to put an atom in the vacant C position, which is right here. So in the case for the generating the cubic close packed crystal, I have an ABC kind of packing. That means this is my A, this is my B, the third layer would be the C layer, which would be right above the vacant area which is generated by this straw. So I put an atom right here in the vacant position. Now I propagate this structure infinitely and I get an ABC kind of a packing. As I mentioned, the important and surprising fact is the generation of the fourfold. So, let us see how the fourfold is generated by putting together A, B, C layers. So, for instance, suppose I call this the A layer, or let me start with a single atom in the A layer. I call this the A layer, my second layer. So, you can see here, you can see from the other camera angle, this is my A position and this is my B position. Okay. So, I got my B position here, and I put the next layer with atoms in the C position, which would be like this. I have specifically cut these planes along. I have not taken infinite planes. What I have done is that I have taken certain section of these planes. Actually, as you can see, these planes are infinite planes with this, have this kind of a orientation running across in all dimension, in the 2 dimensions infinitely, but I have taken a portion of this to illustrate the point. Now, I have an A layer, I have this B layer, I have this C layer, and finally I put an A layer above that. Now, I am just using single ball to generate the A layer, but it would be no different from these layers, but the origin of this layer would be at this atom. Now, I have done this ABC packing, I can go infinitely, but to illustrate the important point, now you can see this configuration has a 3-fold symmetry. So, now my axis, which is coming outward from this, has got a 3-fold symmetry, and more precisely it has got a 3-bar kind of a symmetry. Now to understand that how the 4-fold was generated, I rotate this whole configuration and I can clearly see this is now a unit cell of the cubic close packed structure, which is conventionally drawn, wherein now my central atom is this atom coming outward is the 4-fold axis, and this was the original 3-fold or a 3-bar kind of an axis. So, this is my 4-fold axis. As it is clearly seen, now I can actually visualize this ABC packing as this conventional unit cell of the cubic close packed structure. And to show the wireframe model of the same thing which we have seen before, which I will show from a different camera angle. So, you can see this is my structure which I have generated, the ABC kind of structure, but I have to look along that structure along my body diagonal. So, the ABC packing was along the body diagonal of this cube, which runs like this. This is my body diagonal of the cube, and therefore, I got ABC packing along this direction, and these are the one-on-one kind of planes. So, you can see this plane here, and the next plane is this connecting these atoms. Finally, the top one is another. Let us next consider the primitive unit cell of the FCC crystal structure, in other words the cubic close packed crystal structure. The primitive unit cell is shown by this red and green outlines. If I were to consider the lattice parameters of such a unit cell, you would see that A is equal to B is equal to C, and what are these vectors now? The A vectors, they connect the atom in the 0 0 0 position to an atom in the half 0 0 position. So, A equal to B equal to C, and all the angles, for instance the alpha angle, which would be the angle between this and this vector, the alpha, the beta and the gamma all will be equal, but will not be equal to 90 degrees. So, merely based on the shape of the unit cell, one might be tempted to think this is actually a trigonal or rhombohedral unit cell, but actually this is the primitive unit cell of the cubic close packed structure. Now, the important point to note is that this obviously has an 1/4 the volume as that of the primitive, non-primitive, quadruply non-primitive unit cell, because the quadruply non-primitive unit cell has 4 atoms per unit cell, this is 1 atom per unit cell, therefore, it has 1/4 the volume as that of the conventional unit cell for the FCC structure. Now, the other important point to note that we already seen that this looks like a very distorted kind of an parallelepiped, but we have seen that all parallelepipeds are space filling. So, this rhombohedron, though it may not be obvious from this picture, is actually a space filling solid. Now, another important point to be noted, which we will use later to understand this structure, is the fact that this unit cell can be thought of as made of one regular tetrahedron with vertices as this and this point, an octahedron, a regular octahedron with its center at 0 0 0, this is the center of the octahedron, with the atoms making up the octahedron as these vertices of these green lines. So, this can be thought of as 2 tetrahedra plus 1 octahedra. Now, the reason we usually do not choose this unit cell for the cubic structure is because the unit cell itself has lower symmetry than the crystal which as you can see has a 4-fold symmetry and actually has a 4 by m 3 bar 2 by m point group symmetry. So we will take up the same structure using a model so that we can understand it slightly better. So I have here with me a wireframe model of the same structure showing the primitive unit cell of the cubic close-packed structure. So as you can see here that the primitive unit cell is oriented along the 1 1 1 direction of the cube, and the 1 1 1 direction is the direction along which the centers of the tetrahedron, which is now in the blue and red outlines, the other tetrahedron which is also in blue and red outlines. So let me rotate myself a little bit. So in the green background you can see this is my blue outline, this is my red outline. So this is my tetrahedron with, and then you have the central octahedron which consists of 8 faces and which is centered at the 0 0 0 position. So later on we will see that these octahedra and tetrahedra can be the centers or the voids in the cubic close-packed structure. So you can clearly see this is now the new rhombohedral or the unit cell which has got trigonal kind of geometry. In these slides we should note often we color the atoms differently, but all atoms are the same. So they are not different atoms, they have been colored only for better visualization of the structure. Now let us get down to the next stage, which is the coordination polyhedron, and the coordination polyhedron for the cubic close-packed structure is a cube-octahedron. So two aspects come in when we talk about the coordination polyhedron. Number, of course, the coordination number, which is 12, and as I pointed out, around a given sphere, if you want to touch maximum number of spheres of the same size, the number cannot exceed 12. Therefore, this is the maximum number you can get, and therefore that is what is achieved in both the cubic close-packed structure and, as we shall see later, the hexagonal close-packed structure. The second thing, of course, is the shape of the coordination polyhedron. The shape of the coordination polyhedron is a cube-octahedron. A cube-octahedron has got such a name because it is exactly between a cube and an octahedron. I can take a cube and then I truncate one of its faces. That means I cut one of its faces. That means I can take a cube like this and then I can cut its vertices. Now if I cut deep enough, then I will be cutting into these edges which were originally the vertices of the cube. Now I cut deep enough, then you will see that these faces which are cut faces become triangular, and the remaining face, which if I cut little bit, these faces, blue faces, will be hexagonal, but I cut deep enough, they will become squares, and therefore I get a cube octahedron. Now in terms of the simple rotational symmetries, the cube octahedron is exactly identical to that of a cube and is the coordination polyhedron in the cubic close-packed structure. Now if you want to visualize the cube octahedron, here it has been shown between 8 unit cells. You can see, take any atom in the FCC lattice or any lattice position and place an atom, and you will see that you will find a cube octahedron around it. So it could be an atom sitting on the vertex of the cubic unit cell, or it could be the atom sitting in the face centering position. As you know, these are both lattice points and therefore they are exactly equivalent, and you get a cube octahedron as the coordination polyhedron. Now before we go to the hexagonal close-packed structure, I will show you models of how this close-packed cube octahedra or the coordination cube octahedra is formed. So I have here 2 unit cells of the cubic close-packed structure in the conventional representation, and you can see that the central sphere, which is located exactly between the 2 unit cells, has a coordination polyhedron, which is the cube octahedron. And as you can see, the cube octahedron has square and triangular faces. These triangular faces are the centers, the opposite set of triangular faces will be the centers of the 3-fold axis, and this will continue to be the seat of the 4-fold axis. As I can see, this will be the seat of the 4-fold axis, and this will be the seat of the 3-fold axis. Now even though I have chosen, as I said, the central atom here, the atom between the 2 unit cells, to be the center of the cube octahedron, I can choose any atom in this cubic close-packed structure, and the coordination polyhedron I would obtain would be a cube octahedron. Another point to be noted here, which we shall see in some other solids is violated, is that every atom is exactly located at the same distance from the central atom, which is root 2 a by 2. So this atom is located root 2 a by 2, this is located at root 2 a by 2, this is located at root 2 a by 2, and this is also located at root 2 a by 2. So all of them are located at the same distance from the central atom, and the coordination polyhedron is a cube octahedron. This kind of a structure later on, as we shall see, will be useful in some of the calculations we can make with the cubic close packed crystal. Now returning to the picture here, we have to again note that all atoms are identical. We just colored them for better visualization of the structure. The second kind of structure which we can generate by packing of these close packed hexagonal layers is the hexagonal close packed crystal structure. Actually, these two crystal structures, though we have picked them up in this particular lecture, are nothing but two of the infinite set of possibilities. So, why are they infinite set of possibilities? Let me explain them on the board. For instance, suppose I start with an A layer. I have two choices for the second layer, which are B and C. Having chosen B as the second layer, I would have two choices for the third layer, which would be A and C. Similarly, for the C layer, I would have a choice of A and B. Having chosen the third layer as, so this is my layer 1, this is my layer 2 and this is my layer 3, I have again choices for the fourth layer as B and C, and for the fifth layer, for instance, having taken this path, would be an and I can go ad infinitum in my choice of various layers. But the most common crystal structures which are found in nature are these two kind of packings, which is nothing but my AB packing, which is this branch of my tree, and the second kind of packing is the one which starts here. So, I have let me draw a border here. Is the second kind of packing, which is the one we already seen, is the A B C kind of a packing going to infinity. So, these are the two common structures, but by no means these are the only two possibilities, though often you would find that many of these other possibilities actually do not exist in nature, but these are the two common possibilities, the one outlined in blue and the one outlined in red. But in general, we have infinite set of possibilities of close packed crystals which you can form by starting with a hexagonal close packed layer. And the one which you are now considering is the simplest of the lot, which is outlined in the blue in the board in blue color, which is the AB kind of packing, and the crystal structure we obtain is the what is known as a hexagonal close packed crystal. So, as before, we shall take up the hexagonal layer, a close packed layer which we call the A layer, and then we will generate the whole structure. Later on we will see that this structure actually, this layer is actually the 0001 kind of a plane in the hexagonal close packed crystal. And we have already seen that many crystals actually adopt this HCP structure, and some of the common examples are zinc, titanium and cadmium. So, let us see how this structure works out. You got this brown layer which is the A layer, we choose the next layer which is a B layer, but the third layer I go directly above the A layer, and therefore I use the same color, and therefore I get an AB kind of packing, which is the hexagonal close packed crystal. So, we start with the A layer, put a B layer, but then instead of going to the C layer, we put the layer right above the third layer, right above the A layer, and therefore we get an AB kind of packing, and we will notice in this case that the C layer remains completely vacant. That means, if you were to pass a ray of light through the C layer, it will completely pass through the C layer. And this vacant position, which is a C layer, as we shall see, is an important from the point of view of why this hexagonal close packed crystal is actually called an hexagonal close packed crystal. Now, before I take up the conventional representation of the unit cell, let me go down to the model to explain the concept we have just now seen, which is the AB kind of packing. So, here we have, as before, a layer, a truncated part of the hexagonal layer, and I call this the A set of atoms. So, I put my atoms in the B position, and that means that I leave my C position, which is here vacant. Now, to make the third layer, I will take the same set of planes and put it exactly above the A layer, and therefore I get an AB kind of a packing. I will continue this ad infinitum. In other words, the fourth layer would be exactly above the layer above that, and the fifth layer would be again a layer which is above the A layer, which is what would look like this. But let me look at the structure a little more carefully, which is shown by an alternate model which is kept here, which shows the AB kind of packing. Now, as I mentioned, when you do an AB kind of packing, the C positions, which I mark here with the red straw, remains completely vacant, and actually you can see that a vector can pass right through this C layer. So, all my C positions are completely vacant. Now, an important point to be noted at this stage is that even in the AB kind of packing, my original hexagonal symmetry, which is 6-fold symmetry, has been destroyed, because this is now because of the presence of these additional atoms in the central positions, and therefore, what I have here, the rotational axis at the passing through this is merely a 3-fold. That raises an important question, that even though I have only a 3-fold axis, why do I call this an hexagonal close-packed crystal, and why don't I, for instance, call this a trigonal close-packed crystal, because it has only got a 3-fold rotation axis. So, this ABC and both ABC packing and also the AB packing destroys my 6-fold symmetry present in the individual layers, like if I take an individual layer like this, and I got only a 3-fold symmetry left. So, why do I call this an hexagonal close-packed crystal? And as we know that crystals are named based on the symmetry and not based on the geometry of the unit cell, and why do I still call this an hexagonal close-packed crystal? So, this question we will answer later. So, this is the conventional unit cell of the hexagonal close-packed crystal, wherein you have the A layer, the B layer, and again the A layer right above the A layer, which was the first layer which I started off. Now, as I have told before, this actually shows 3 unit cells of the hexagonal close-packed crystal, and the actual unit cell is nothing but this rhombic prism. Okay. Now, a few things have to be noted. We have seen already that there is only one kind of an hexagonal lattice, the simple hexagonal lattice. So, now how do I accommodate this presence of this additional atom within the unit cell, and where exactly is this additional atom located within the unit cell? So, these are a couple of questions we can ask, but before we do that, we note that the lattice is hexagonal, and now the motif is an atom at 0 0 0 and also another atom which is located at 2/3 along the x axis, 2/3 along, that is the A1 axis, 2/3 along the 1/3 along the A2 axis, and half along the C axis. So, this is my additional atom, and that atom goes part of the motif and is not part of the lattice itself. Therefore, if this is my lattice point, then this atom here goes part of the motif. And my conventional unit cell, as you can see here, is the rhombic prism, which is outlined in the blue color. So, I have my simple hexagonal lattice and a 2-atom motif, and as before I have to put exactly this kind of a motif in identical orientation at each lattice point to get the hexagonal close-packed crystal. And as I pointed out, this hexagonal close-packed crystal, if I look at pure rotational symmetries, has got a 3-fold rotation only. Now, just to re-emphasize some of the points which we have considered so far, the hexagonal 6-fold symmetry present in the A layer is lost on AB packing. The crystal, now answering the important question, the crystal is called an hexagonal crystal because there is a 6-3 screw axis which passes through the vacant C sites. As I mentioned, the vacant C sites was an importance for our consideration, and the reason I mentioned that was for this reason, that actually you got a 6-3 screw axis which passes through the vacant C sites, and you already have seen that vacant C sites in the 0 0 0 1 projection. Now, even though this is not a pure rotational 6-fold axis, it still has a 6 in it, and that is why these crystals which have a 6-3 screw axis are classified under the hexagonal class. We also seen that this is one of the closest packing crystals possible, which is 74% packing of volume. An additional point to be noted is that the atom which is inside the unit cell is not part of the lattice, and that means the center of that atom is not a lattice point, but is actually part of the motif. So, these are some of the important considerations, and we can take a further views to understand the same crystal structure. Here we are presenting nothing new, no new concepts, but we are just trying to visualize the crystal structure in various ways, and one of the important ways to see where exactly this additional atom is located. So you can take my rhombic prism, divide it into first of all into a half, therefore I get my triangular prism, and this triangular prism I can divide into half along the c axis, therefore I get the midplane of the, this is my midplane of the triangular prism, and this atom is located on the midplane and at the centroid of this triangle, which is vertices as marked here. So this atom is located at the centroid of this triangle, which is nothing but the midplane of the half the triangular prism. So this is where the additional atom is located, and next we will try to calculate what is known as the ideal C by A ratio for an hexagonal close packed crystal. Okay. Now we have just put we have packed the layers along the C direction, and therefore if you have perfect spheres, there is a mathematical value for this C based on the atomic diameters. So now I have the hexagonal lattice decorated with the 2 atom motif at 0, 0, 0 and at 2/3, 1/3, half. Now we will see that the ideal structure with spherical motifs has a C by ratio which is 1.632. So let us see how this 1.632 comes about. Now to calculate that, let me consider a tetrahedron which is formed by this atom and the atoms which are located at these vertices. So I make a tetrahedron out of these atoms, because I join these atoms and the base to form a tetrahedron. So I have a tetrahedron and I consider that tetrahedron, and the vertex of that tetrahedron I call V. Now because it is a regular tetrahedron, CV, C is the centroid of this tetrahedron, CV is √6/4a, where a is this edge, cell edge length. Any of these cell edge lengths is a. CF is √16/12a, in other words 1/3 of that value, and H is nothing but half the C value. That means my C length is a length from, this is my C value, and this H is half that. So it is the midplane. So it is the distance of the midplane. So my H as marked here is half, which is nothing but FV is half the C value, and H is equal to CF plus VC, which is √2/3a, root of 2/3a, and the C by A value I can calculate is nothing but 2H. As I said, H is half the value of C, so it is 2H/A, which is twice root of 2/3, which is 1.632. So this calculation of course is a simple geometry calculation which you can perform independently, but the important point we noted here is the value we have calculated. That is, the ideal C by ratio is 1.632. Now if I look at this ideal C by ratios of some of the common metals which crystallize in the hexagonal close pack structure, like cadmium, zinc, magnesium, zirconium, titanium and beryllium, you would notice that even in this list there is just one which comes even close, which is magnesium, which has got an C by ratio of 1.624. In other words, most of the metals which have the hexagonal close pack crystal structure do not have an ideal C by ratio. In other words, how did I get this ideal C by ratio? By assuming that all my atoms are hard spheres, and I get an packing which is an ABAB kind of packing. So in nature this kind of an assumption is not true, in other words it is not valid 100%, and therefore I can get a non-ideal C by ratio for most of the metals. Some of the C by ratios are larger, like for instance cadmium has 1.886, zinc has a larger value, but some of the metals like beryllium have a smaller C by ratio. And now what does a smaller C by ratio mean? It means that I am squashing the hexagon downward. A larger C by ratio means I am expanding the hexagon. So let me take up a model to show you what is this hexagonal close pack structure. So I have a model here which shows the hexagonal close pack structure. So I have atoms in the A layer, the B layer which is the middle layer, and the layer which is above, which is the A layer right above the basal layer. And this, as you can see, is nothing but the 0, 0, 0, 1 plane of the hexagonal close pack structure, and my basis vectors are the vectors along, say for instance this is my A1, this would be my A2, so this is my A1, this is my A2, and the vertical vector is the C vector which is above. This, as we said, is part of the motif, and therefore my 2 atom motif would be a sphere here and a sphere here, which goes on to decorate every lattice point. So I would put a 2 atom sphere here, here and so forth, and some of them would sit within this rhombic unit cell and some of them would not sit within the rhombic unit cell. Now, as I mentioned, this kind of a structure is what has got, let me show from the side, has got approximately the ideal C/by ratio. But as I told you, real hexagonal close packed crystals can have a C/by ratio which is extended, that means it could be larger or smaller, and that means that my spheres cannot be assumed to be the hard sphere model of atoms is no longer valid. Now, the tetrahedron which I considered can also be seen nicely in this model of the hexagonal close packed structure, wherein of course there are more than one unit cell here, but you can clearly see the tetrahedron which I was mentioning to calculate my ideal C/by ratio are these 4 atoms which go on to form the tetrahedron, from which I made my ideal C/by ratio calculation. We will return to this model when we talk about voids in hexagonal close packed crystals. The next important crystal we consider, and before that I have a question from Ravi.
What will the effect of deviation from the ideal C/by ratio 1.63 to the close packing of the crystal?
Okay, very good question, very good question. Obviously, if you have a deviation from the, there are 2 important questions we can ask here. One is of course the question which you asked is what is the packing fraction, how is it affected by a non-ideal C/by ratio, and number 2 is of course the important question, what is its consequence on the properties of the crystal. The first one, obviously it will deviate from the ideal packing fraction. So ideal packing fraction is assumed using hard spheres, and if there is a non-ideal C/by ratio, obviously this number would be affected, the packing fraction would be affected. The second question is the impact on properties. Now we will see typically if these basal planes are the slip planes in, another when we are talking about plasticity will be the slip planes, and if you have these basal planes separated out, then there will be basal slip would be promoted. If you have these planes squashed together, then basal slip would be would not be that much easy to take place. So the next structure we take up is what is known as the BCC crystal, which we know is a monoatomic or a monoionic decoration of the BCC lattice. So we have seen this structure before, and there are 2 views of the structure right here, and you can see that there is 2 atoms per unit cell. That means it is a doubly non-primitive crystal structure. And the important point we already noted, and we will re-emphasize that this is not a close packed structure, and we will see a little more about this later. And more importantly, it has got no close packed planes. In the case of the FCC and HCP, we started off with close packed planes, and those planes, assuming of course an ideal C/by ratio in the case of hexagonal, that these planes remain close packed planes when you continue to make the crystal out of those close packed planes. But in the case of BCC crystal, the construction is not done the way we have done the FCC or the CCP and the HCP crystals, and therefore this crystal structure has no close packed planes. However, the 1-1-1 direction is a close packed direction. That means the atoms touch along the 1-1-1 direction. This is my origin, for instance, and this is the other vertex. So my 1-1-1 direction will be the direction connecting these, and the atoms touch along the 1-1-1 directions, and therefore that is a close packed direction in the BCC crystal. So when I mention BCC crystal without any other qualification, and we will see later of examples that we should be a little careful in this regard. When I say BCC crystal, what I mean is a monoatomic decoration of the, or a monoionic decoration of the BCC lattice, and such a structure, to re-emphasize, is not a close packed structure, has no close packed planes, but still continues to have a close packed direction. Some of the common metals which or elements which solidifying this crystal structure are tungsten, iron below 910 degrees Celsius, which is called alpha iron, and some important elements like sodium and potassium. This is, in this case of course it is obvious that the lattice is BCC, and all I have is a single atom decorating the BCC lattice. Now the coordination polyhedron for BCC is a different kind of a polyhedron, and we have already dealt with this polyhedron, or we have encountered this polyhedron in the context of the space filling. We saw that cube is a regular solid which has got space filling properties. We saw that there are 2 non-regular solids, or 2 important non-regular solids which have space filling property. One is the tetrachedecahedron, other one is the rhombic dodecahedron, and this rhombic dodecahedron is the solid you see here, or the which is the coordination polyhedron for the BCC structure. So I take any atom, it could be of course the one which is shaded in blue or the one shaded in red, both of them are identical atoms, and if I construct a polyhedron around it, it would be a rhombic dodecahedron. But the important point to be noted here is that even though the rhombic dodecahedron is made up of a single kind of a face, which is a rhombus, if I take a central atom, which is here, of course this is my central atom, then all the atoms are not located at the same distance from the central atom. This is an important point to note. For instance, the atoms which are shown in blue are located at a distance of root 3 by 2a from the central atom, and the ones shown in brown are located at a distance a. That means the coordination polyhedron is now not only made up of nearest neighbors but also next nearest neighbors. So that means there are two kinds of distances which I need to encounter, a and root 3 by 2a. So this is what. So of course this a is root 3 by 2 has a bracket here, so therefore this is root 3 by 2 into a. So let me look at a model of the rhombic dodecahedron so that we understand how does this shape look like, and then we will proceed to the other further pictures of the BCC crystal. So I have here a model of the rhombic dodecahedron, and as you can see, this is not one of the regular solids, it is not a platonic solid, and this is got identical faces, this solid. For instance, all the faces are rhombus, but the kind of vertices it's got are two types. There are vertices which are 3 connecting, as you can see this vertex is a 3 connecting vertex which is in green, and there are also red vertices which are 4 connecting vertices. So there are 4 connections from these vertices. So the rhombic dodecahedron is it's a very special kind of a solid which is a space filling solid. It's not a regular solid, it has got identical kind of faces but 2 kinds of vertices, the 3 connecting vertex and the 4 connecting vertex. So this is an important solid as far as geometry goes, which is the rhombic dodecahedron, and it is called a dodecahedron because it is called 12 faces, which you can see from this diagram. It has got 12 faces, 4 above, 4 in the mid plane and 4 below. So this has got it's a rhombic dodecahedron. Now this diagram below, for instance, shows us the touching direction, which is the 1, 1, 1 direction along which atoms touch. Again, you should note that all atoms are identical and they have just been shaded for clarity, and this is a slight transparent model to show that where the central atom sits and how the atoms touch one another. Suppose I look along the 1, 1, 0 direction, then you will see, and of course I remove the atoms which are in front of this blue sphere, then I can see the relative position of this blue sphere which is in the body centering position with respect to the other spheres. Of course, like in many of the other cases, if I had not chosen my origin here, I would have chosen my origin at the blue sphere, the structure would be totally unaltered, and this would, in other words, these atoms now which are in the vertices of this cube will all become body centering position atoms. Now we should note that whenever we deal with a new structure, it is very, very important that we actually look at the structure from various points of view, try to understand some of these concepts we have been outlining again and again, the direction of close packing, the direction of touching, and which of the atoms touch each other, which of them do not touch each other, and also the concept of the coordination polyhedron. So that is a very important concept.